Oh, goodness.
Okay, we need to talk about this.
There was a calculator on the desk.
Let's talk about your calculator answers today. A lot of times when you guys get answers, you know, you might see an answer like this. 0.123, we're just rounding to the nearest thousand, 3 decimals. What would that be as a percentage?
1%.
12.3%. Now, some people like to put their answers as percent, some like to put them as decimals. It doesn't matter to me. I would just rather leave it in a decimal form and just say 0.123. Okay? Now, some of your calculators are going to do this today. When your probabilities, maybe not so much today, but when your probabilities get real small, you might see this on your calculator. That means that your calculator, if you see 0.000 on your calculator, that doesn't mean your answer is 0. It just means that your answer is smaller than the nearest thousand. What your calculator is doing is putting this in scientific notation. This is not acceptable. Don't leave it like this. So if your calculator, if you see this E, I want you to write it as 1.23 times 10 to the negative 4. Put it in proper scientific form. E is just base 10. Or some people will do this and say, well, I'll just move my decimal over 4 places. 1, 2, 3, 4. So I would accept this and I would accept that. Okay? This means that there's a probability of it happening, it's just that it's very small. Like the probability of getting dealt 4 of a kind is very small. It's going to be smaller than this. And so you're going to get really small numbers from time to time, okay? So realize that. Now, if you get this on your calculators today, I don't think anybody's going to want to write 15 zeros out, okay? I don't think you want to go 0.0000 15 times and then 756. So I'm okay with you putting it in scientific notation. Okay, probably rather do that anyway. All right, so realize that that could show up. Put your answers in proper form. If I see E to the negative 4, I'll take a point away. I mean, that's just not proper. That's our calculators put it in scientific notation. Okay? All right, well, let's talk about types of probability. There are 3 types. A lot of your test over this unit is I just give you scenarios and you tell me what kind of probability it is. Okay? The 3 types are what we call classical, empirical, and subjective. So these are the 3 types of probability. Okay? Let's talk about classical first. Classical probability is probability that never changes. It's the same probability day after day, month after month, year after year. The perfect example of this would be cards, the lottery. When you buy a lottery ticket, your chance of winning are the same day after day after day. Okay? Flipping a coin. Okay? If I flip a coin today and get tails, my probability tomorrow of flipping the same coin is still 50%. Okay? It never changes. It's classical probability. It's the same probability day after day after day. Now, here's how you calculate it. The probability of the event is the number of desired outcomes divided by the total number of outcomes. We kind of did this last chapter. Does anybody tell me what part of our test that we did this in? Where did you take the probability or the number of outcomes divided by the total number of outcomes? Close, frequency.
Standard.
Didn't we do that for the relative frequency? Remember making the classes and setting up your tables? Isn't relative frequency the frequency of the road divided by the total number of frequencies? That's this. I mean, that's the frequency of the road divided by the total number. Exact same thing. Okay? So that is classical probability. Let me give you an example of empirical probability.
Hold on.
What?
I'm still writing. Okay, you can go.
So empirical probability is probabilities based off of observations, past records. Okay? This probability will change. Okay? Classical probability never changes. You being dealt the ace of hearts out of a deck is the same today as it is tomorrow. But empirical probability, that is not true. Okay? Here's a couple different examples of empirical probability. And I think we just need to see an example of this. Let's say in my sock drawer, I have 10 black socks. I have 5 white socks. And I have 3 red socks. Okay? I reach in the morning and I just grab a sock. I don't look at it, I just grab a sock. What would be the probability of selecting a black sock? 10 out of
18.
And how many socks do I have in the drawer? 18. So I would just take 10 divided by 18. Let me give you the decimal equivalent. Again, I'd like you to give it to me as a decimal today. 0.556. So I have a 0.556% chance or 55.6% chance of grabbing a black sock. The next day, I don't put my dirty socks back in the drawer, but now I reach in and grab another sock. Okay, the next day. What would be the probability that it's white? Well, how many white socks are in the drawer?
5.
And since I already grabbed the sock out,
17.
17 now. Do you see that that probability changes? Because I grabbed a sock, I wore it, I threw it in the dirty clothes the next day, and I grab a different sock. Okay? If I take 5 divided by 17, I have 0.294 chance. Or a 29.4% chance of that happening. This is empirical. Do you see that my probabilities change time after time after time? Okay? One other thing, and this is a dead giveaway with empirical, is this past records. Okay, let me give you an example of this. Let's say that a company knows, on average, that 10% of its washing machines break down within 6 months. A company knows that 10% of its washing machines break down within 6 months. Is that a guarantee? You know, if I sell 100 machines, does that mean that 10 of them are going to break down? Is that a guarantee? No. Maybe 90 break down. Maybe 0 break down. But do you see it's based off of past studies? So they kind of have an idea of what to expect. It doesn't mean it's going to happen. That's empirical. Okay? The formula is identical. It's the probability of desired, I'll just say number of desired outcomes divided by the total number. So the probability is the same in terms of how we calculate it. The desired amount divided by the total amount. Okay, last one, subjective. These are results from like an educated guess. You see the key word here is a guess. It's an educated guess. Okay. There's no formula for it. It's subjective. Here's an example. I think there's a 40% chance of snow today. Does that mean it could snow? Maybe it doesn't snow. Okay, I think there's a 50% chance of rain today. That doesn't mean that it's going to. Okay, just there's a 50% chance. So this is kind of the best job in the world is a weatherman. I mean, think about it. You could be wrong every day and you still get to go to work every day, okay? You could be wrong every single day. Like, I think it's gonna snow. Oh, we got a snow advisory today and it doesn't even snow at all. But yet he gets to come back to work the next day, okay? If any other job, you could be, if you were wrong like that every time, you'd probably get fired, okay? So predicting weather is subjective. I mean, now, I get it, they have educated guesses and they have a lot of technology, but it's not a science by any means. It's not a guarantee, okay? Let me read you off some scenarios. Just tell me, what do you think it would be? Would it be classical, empirical, or subjective? Here we go. The probability that a voter chosen at random will be younger than 35 years old is 0.3. What do you think? Classical, empirical, or subjective?
Empirical.
That's empirical. Is that based off of past studies? Like, a chance of it happening is 0.3. Doesn't mean it's guaranteed, but it's right around 30%. Okay? How about the probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000?
Classical.
That's classical. Will it ever change? If you have 1,000 tickets, there's only one way to win it, 1 out of 1,000. Okay? The probability that you'll get an A on your next test is 0.9. Let me ask you, is there a formula for me to calculate that at all? I would lean that to be a little bit more subjective. Now, if I had a whole bunch of your test scores, and I know that on average you get around a 90%, could I make that prediction and maybe argue that it's empirical? Because based off of 20 previous test scores, this is what you get. So I could make that, but if it's only like one test or something like that, I would probably lean a little bit more subjective. How about the probability is, wait, never mind. Oh, that's it. Okay. Next thing. Before I get all probability, these are just questions that I missed last week. When you calculate the probability of something, you need to realize that your probability can only fall between those two numbers. Okay? Is there a chance 0 happens?
Yeah.
Yes. Is there a chance of 100 happening?
Yeah.
Yes. So is it possible for you to get the probability of event to be 110%? No. How can you get above 100? So realize that when you guys are calculating all your answers, no answers can be above 100 and no answers below 0. Can't have a negative probability. Good with that? All right.
Yeah.
Let me do cards now.
Oh.
Here we go. Let me give you the information you need for cards. First off, how many cards are in a standard deck of cards?
52.
52 cards.
You want to play 52 cards later?
Okay. How many cards of each suit?
4. Wait.
Or excuse me, well, there's 13 cards. Let's go a little bit narrow. How many suits are there?
4.
Okay. And what are the suits?
Jack.
So you got hearts,
Diamonds, clubs, and
diamonds,
yeah, spades.
clubs,
Spades.
and spades. Okay, so you have 4 of those. Now, how many of each suit? 13. 52 divided by 4 is 13.
Can we play poker?
Okay. How many of each card? 4 of each card, right? So you have 4 2s, you have 4 3s, 4 4s, 4 5s, etc. Okay. How about face cards? How many face cards are there in a deck? Your face cards are Jack, Queens, and Kings. 12. You have 3 of each. You have a Jack, Queen, King, times 4 is 12 face cards. Because they may ask you, what's the probability of being dealt a face card out of a standard deck of cards? Well, it'd be 12 out of 52. Okay? I don't think we have to worry about poker hands right yet. Okay? I think everybody understands a 4 of a kind. I think everybody understands a 3 of a kind. Maybe a full house. What's a full house?
I have no idea.
2 cards are the same. I mean,
2 of the same and
same, and then 3 is the same.
3. So you have 3 of one card, 2 of another. Okay? So a full house is when you have like 3 kings and 2 queens. 3 of one, 2 of another. Okay? Is everybody good with 2 pair? 2 pair means you have 2 2s and 2 3s. You have 2 pairs. Okay? A straight. We all good with the straight? 4, 5, 6, 7. 5 cards in a row. A straight. Is everybody familiar with a flush? What's a flush? 5 cards of the same suit. Yes, Kyle.
Should we play poker at the last new school? This class?
No, because you're not going to be any good.
Okay, no. Okay.
You know, I just
You don't got
put
12.
cookies on it and it's gone.
You don't got 12 mil on your poker rules.
Are we good with a royal flush?
No.
Oh, yeah.
A royal flush would be 10, queen, king,
All face cards.
10, jack, queen, king, ace. Okay, of the same suit. So a royal flush, could you have just a straight flush? Could you have a 2, 3, 4, 5? That works too, of the same suit. So the ones that you really need to know, I mean the 4 of a kinds, 3 of a kinds, those are easy. A full house and a flush, maybe those ones you're not quite familiar with. Or a royal flush or a straight flush, okay? All right, so like part of what you guys do today is pretty darn easy. Like out of a standard deck of cards, I might say, what is the probability of being dealt we'll go a face card. Okay, well how many face cards in the deck? 12 out of?
52.
Okay, so again, I would like your answers as a decimal. So if I just take 12 divided by 52,
1, 2, 3, 1.
so I have like a 23.1% chance of that happening. So a lot of the probability that you guys do today is very basic probability. It's just, what's the probability of getting a 2 out of a standard deck of cards? 4 out of 52.
Are they all card questions?
A lot of them are. What's the probability of being a red, oh, I didn't talk about that, a red 2? Well, how many red 2s are there in the deck?
There's 2.
2.
No.
Diamonds and
Hearts.
hearts. So I don't know if we need to say this. This is red. This diamonds are red. Clubs are black.
So 26 red cards and 26 black cards.
Exactly. So I may ask you, what's the probability of being dealt a red ace? Well, there's the ace of hearts and the ace of diamonds, so you'd have 2 out of 52 chance of that happening. Good with that? What type of probability would you say this is? Classical, empirical, or subjective? Definitely classical, because it's never going to change, right? It's the same answers day after day after day. Okay? We good? Okay, one last thing. I am just going to jump a little bit, not much, but I do want to talk about independent events and dependent events, and then we'll stop there, and then we'll do the rest of it tomorrow. Okay, I can squeeze it right here. So I'm going to dive into section 3.2, and we're just going to talk about these 2 things. There's no formulas or anything. It's just terminology. So I just want you to make sure that you understand the difference. And that's it. Okay. Here we go. 2 events are independent if one Okay. Two events are independent if one outcome does not affect the outcome of another. Okay, that means they're independent events. Here's the simplest example I could give you. I flip a coin and then I roll a die. Does me flipping a coin have any outcome when I roll the die? No, they're independent of each other. One does not affect the other. Okay, they're independent events. Okay? Now, dependent events is just the opposite. If one outcome does affect the outcome of another.
Like your socks in the drawer.
Yes. Does anybody have another? How could I do? Who could give me an example of dependent events using cards?
So you took out an ace. and
I took out an ace.
And then you rolled again.
I set it down, and then I select another card. Doesn't that affect the outcome of my second card? Because now there's only 51 cards in the deck. Okay? So that you really have to read the questions carefully, because they'll say, hey, you take a standard deck of cards, you select a card, you look at it, you put it back in the deck. Well, now it's now they're independent events. One does not affect the outcome of the other. But if I say you look at it and you set it down, then that does affect the outcome of the next card. Okay? So those are dependent events. Here's how your book likes to word it. You speeding in, you're speeding in on the freeway and you get a speeding ticket. Would you consider that independent or dependent events?
It's kind of dependent.
It's dependent. Why did you get a speeding ticket? Because you were speeding. It makes sense that one affected the outcome of the other, right? They're dependent events, okay? Now they might say selecting a boy with blue eyes and selecting a girl with green eyes. Do those have anything in common with each other? No, I would consider those independent events. Make sense?
Yeah.
Okay, all right, we'll stop there. There's this section is where we start to do card problems and like playing like 5-card poker and stuff like that. So we'll worry about that tomorrow. I just want you to be able to do these definitions today.
So would you get to play with it?
Well, you don't get to play it, you get to calculate the probabilities. Okay, here we go.
That's what you said.
So let's go back to page 140. We can go back now and pick up some of the questions we skipped.
Yay. Wait,
Okay.
like what?
We could do 2 and 3. We already did 11 through 4. Oh, so we can do 29 through 34. This is where you're starting to do probabilities. We can do 41 through 46. Here's all you're doing in that section. They're going to give you a statement. You just tell me if it's classical, empirical, or subjective. You don't need to explain your answers. Just tell me what it is. Okay? Let me see if there's anything else on here.
I think we're okay.
Oh, we could do a spinny wheel. Too late. 51 through 54. Spinny
Oh
wheel.
my gosh.
That's more than one.
That's easy.
The spinning
A spinny wheel. If you spin it, what's the probability of getting it blue?
I don't know.
Pretty
but I don't
easy.
know what color
You gotta look at it. Okay.
You're killing me.
Last, well, we're not done yet.
What?
I still think.
Boy, you can't.
2 hours.
Oh my god.
Can't even reach the other side.
There you go. This last section, they're gonna give you statements and you just tell me if they're independent or dependent. That's it. Okay? Remember, when you guys get to 29 through 34 and 41 through 46, I need to see your work.
It won't even.
It could be as simple as I took 1 divided by 4 and my answer is 0.25. Okay? When it's short answer questions or definitions, you don't have to show work on that. Yes, Reese? Nope.
These desks are not big enough.
What are you talking about? This
They're
is
not big
probably
enough.
too big for you.
Mr. Herndon.
No, look, it's not big enough for all my
Oh,
stuff.
he needs a more tabletop.
Yeah.
What was the one or on Thursday?
So Barry, I work on your stuff. What was it yesterday?
It's not right there, right? But yeah.
Well, it is today.
It's Kai, remember?
Oh yeah, you can have more than one. Okay, you ready?
Yeah. so good.
We did page 140,
Oh,
1-4,
Okay, I'm a negative probably. 1-4.
1 and 4, 7, 8, 15 to 20, and then, well, actually, I could just say 15 to 20.
28.
15 to 20. And all these are, the 15 through 20 is sample space questions. Those can be kind of big, but then the rest of them are just
Like her
not
story?
bad at all.
Okay.
I did throw out 17 because there's 52 answers there. So I threw out 17 for you.
Okay.
Sounds good.
Thank you.
Okay. We stopped.
Oh, no, wait.
What?